At the end of this video, you should be able to describe dipole-dipole forces, hydrogen bonding, induced dipoles, and London dispersion forces and their effects on properties such as boiling point and melting point, and explain the shapes of molecules or polyatomic ions using Vesper theory. Chapter 6, Section 5, Intermolecular Forces. As a liquid is heated, the kinetic energy of its particles increases. At the boiling point, the energy is sufficient to overcome the force of attraction between the liquid's particles. The particles pull away from each other and enter the gas phase. Boiling point is therefore a good measure of the force of attraction between particles of liquid. The higher the boiling point, the stronger the forces between the particles. The forces of attraction between molecules are known as intermolecular forces. Intermolecular forces vary in strength, but are generally weaker than bonds that join atoms and molecules, ions in ionic compounds, or metals in solid metals. Compare the boiling points of the metals in ionic compounds in Table 6-7 on page 190 of your text, or on the screen now, with those of the molecular substances listed. Note that the values for ionic compounds and metals are much higher than those for the molecular substances. Molecular polarity and dipole-dipole forces. The strongest intermolecular forces exist between polar molecules. Polar molecules act as tiny dipoles because of their uneven charge distribution. A dipole is created by equal but opposite charges that are separated by a short distance. The direction of a dipole is from the dipole's positive pole to its negative pole. A dipole is represented by an arrow, with a head pointing toward the negative pole and a crossed tail situated at the positive pole. The dipole created by a hydrogen chloride molecule, which has its negative end at the more electronegative chlorine atom, is indicated as follows. The negative region in one polar molecule attracts the positive region in adjacent molecules, and so on throughout a liquid or solid. The forces of attraction between polar molecules are known as dipole-dipole forces. These forces are short-range forces, acting only between nearby molecules. The effect of dipole-dipole forces is reflected, for example, by the significant difference between the boiling points of bromine fluoride, the Br to F bond, and fluorine, the F to F bond. The boiling point of polar bromine fluoride is negative 20 degrees Celsius, whereas the nonpolar fluorine boils at negative 188 degrees Celsius. The dipole-dipole forces responsible for the relatively high boiling point of BRF are illustrated schematically in Figure 6-25 on page 191 of your text, or on the screen now. The polarity of diatomic molecules such as BRF is determined by just one bond. For molecules containing more than two atoms, molecular polarity depends on both the polarity and the orientation of the bond. A molecule of water, for example, has two hydrogen to oxygen bonds in which the more electronegative oxygen atom is the negative pole of each bond. Because the molecule is bent, the polarities of these two bonds combine to make the molecule highly polar, as is shown in Figure 6-26 on page 191 of your text, or on the screen now. An ammonia molecule is also highly polar because the dipoles of the three nitrogen to hydrogen bonds are additive, combining to create a net molecular dipole. In some molecules, individual bond dipoles cancel each other, causing the resulting molecular polarity to be zero. Carbon dioxide and carbon tetrachloride are molecules of this type.
Dipoles cause polar molecules to be attracted to one another. Although the forces involved are relatively weak and short range, they can still have important effects on the properties of many materials. Bromine fluoride is a polar covalent bonded molecule. The slightly charged ends of the bromine fluoride molecule attract the oppositely charged ends of other polar molecules. Because liquid bromine fluoride has these dipole-dipole interactions locking the molecules together, it has a relatively high boiling point. As the liquid heats up, the molecular vibrations become stronger and the dipole-dipole interactions become harder to maintain. Eventually, the bromine fluoride boils. Similar liquids without dipole-dipole interactions will boil at a much lower temperature. Molecular fluorine, for example, which is completely nonpolar, boils at negative 188 degrees Celsius. Without dipole-dipole interactions, the molecules can separate easily.
A polar molecule can induce a dipole in a nonpolar molecule by temporarily attracting its electrons. The result is a short-range intermolecular force that is somewhat weaker than the dipole-dipole force. The force of an induced dipole accounts for the solubility of nonpolar oxygen, O2, in water. The positive pole of a water molecule attracts the outer electrons of an adjacent oxygen molecule. The oxygen molecule then has an induced negative pole on the side toward the water molecule and an induced positive pole on the opposite side. The result is an attraction to the water molecule, as is shown in figure 6-27 on page 192 of your text or on the screen now.
The oxygen dissolved in water is vital to the fish and other aquatic organisms. But how does a nonpolar molecule like oxygen stay dissolved in a polar solvent like water? Let's take a closer look. The positive pole of a water molecule causes a temporary change in the electron distribution of an oxygen molecule. The oxygen molecule now has a dipole, with the negative portion of the oxygen dipole facing the positive pole of the water molecule. Dipole-dipole interactions allow the nonpolar oxygen molecule to be weakly attracted to the polar water molecule and remain in solution.
Hydrogen bonding. Some hydrogen-containing compounds such as hydrogen fluoride, HF, water, H2O, and ammonia, NH3, have unusually high boiling points. This is explained by the presence of a particularly strong type of dipole-dipole force. In compounds containing hydrogen to fluorine bonds, oxygen to hydrogen bonds, or hydrogen to nitrogen bonds, the large electronegativity differences between hydrogen atoms and fluorine, oxygen, or nitrogen atoms make the bonds connecting them highly polar. This gives the hydrogen atom a positive charge that is almost half as large as that of a proton. Moreover, the small size of the hydrogen atom allows the atom to come very close to an unshared pair of electrons on an adjacent molecule. The intermolecular force in which a hydrogen atom is bonded to a highly electronegative atom is attracted to an unshared pair of electrons of an electronegative atom in a nearby molecule is known as hydrogen bonding. Hydrogen bonds are usually represented by dotted lines connecting the hydrogen bonded hydrogen to the unshared electron pair of the electronegative atom to which it is attracted. An excellent example of hydrogen bonding is that which occurs between water molecules. The strong hydrogen bonding between water molecules accounts for many of water's characteristic properties. Hydrogen bonds are usually represented, again, by dotted lines connecting the hydrogen bonded hydrogen to the unshared electron pair of the electronegative atom to which it is attracted, as is illustrated for water in figure 6-28 on page 192 of your text or on the screen now. The effect of hydrogen bonding can be seen by comparing the boiling points in table 6-7 on page 190 of your text or on the screen again. Look at phosphine, pH3, compared with hydrogen bonded ammonia, NH3. How does hydrogen sulfide, H2S, compare with the strongly hydrogen bonded water, H2O? London dispersion forces. Even noble gas atoms and molecules that are nonpolar experience a weak intermolecular attraction. In any atom or molecule, polar or nonpolar, the electrons are in continuous motion. As a result, at any instant, the electron distribution may be slightly uneven. The momentary uneven charge creates a positive pole in one part of the atom and a negative pole in the other. This temporary dipole can then induce a dipole in an adjacent atom or molecule. The two are held together for an instant by a weak attraction between the temporary dipoles, as is illustrated in Figure 6-29 on page 193 of your text, or on the screen now. The intermolecular attractions resulting from the constant motion of electrons and the creation of instantaneous dipoles are called London dispersion forces, after Fritz London, who first proposed their existence in 1930. London forces act between all atoms and molecules, but they are the only intermolecular forces acting among noble gas atoms and nonpolar molecules. This fact is reflected in the low boiling points of the noble gases and nonpolar molecular compounds listed in Table 6-7 on page 90 of your text. Because London forces are dependent on the motion of electrons, their strength increases with the number of electrons in the attracting atoms or molecules. In other words, London forces increase with increasing atomic or molar mass. This trend can be seen by comparing the boiling points of the gases helium, He, and argon, Ar, hydrogen, H2, and oxygen, O2, and chlorine, Cl2, and bromine, Br2.
In any atom, the random motion of electrons around the nucleus can create a positive pole in one part of the atom and a negative pole in another part. If another atom is located nearby, the temporary dipole can induce a dipole in it as well. The two atoms are held together for an instant by the weak attraction between the temporary dipoles, before separating again as electron motion causes the dipoles to disappear.
At this point, you should be able to describe dipole-dipole forces, hydrogen bonding, induced dipoles, and London dispersion forces and their effects on properties such as boiling and melting points, and explain the shapes of molecules or polyatomic ions using VSEPR theory.